Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California, and this is an augmented video lecture for differential equations. And this assumes that you've had a light introduction to differential equations, but you still do not know how to solve differential equations. We will also assume here that you know a little bit about critical points, and that you know, because I'm going to use this here, a little something about phase portraits and the behavior of solutions at critical points. So let me go ahead and just rewrite a couple things concerning critical points and phase portraits. Actually, I should probably read this. We're going to assume that we have a solution to this differential equation, this first order differential equation, which is in format autonomous. So let me go ahead and showcase that. This form dy dx is equal to a function of y means that your differential equation is autonomous. And as you can see, I just wrote out a recall of that first order autonomous definition. And we're going to assume, let's see, that y1, like I said, is a solution to that autonomous first order differential equation, and that c1 and c2 are two consecutive critical points. That's what that CP stands for. Let me go ahead and write out a recall of critical points so that we now know, or we recall, that C is a critical point for an ODE dy dx is equal to a function of y, an autonomous first order ODE, if when you plug C into the right-hand side, you get 0. Or in other words, that our derivative is 0 at C. So that's kind of, maybe I should write that down. So that will imply that dy dx, when y is equal to c, is equal to 0. Okay, so we happen to know the slope of our solutions will be 0 when y is 0. And this definition actually works really nicely with our Calc 1 definition of a critical point. There's a little bit more in the Calc 1 definition, right? The Calc 1 definition of a critical point says that the derivative is 0 or does not exist. So this doesn't have that in there, but that doesn't matter. So going back to the original question here, we're going to assume that C1 and C2 are two critical points, where just without loss of generality, that C1 is less than C2, so there's some order to it. And we also will note that our solution is between those two critical points and that y1 is positive. Now that I'm thinking about that, that y sub 1 should more be like this. F of y sub 1 should be positive. And again, that's not actually a strict requirement. We could have f of y sub 1 be strictly negative, but it's of one sign. That's what's important here. So I don't know why I had written in there y sub 1 is positive, but it's f of y sub 1. So in other words, the derivative is positive on that region. Now, before I get into the rest of this question, I want to recall again the prereq skill here that we know what a phase portrait looks like. And so I'm going to draw out a phase portrait for this situation. I'm going to scroll up a little bit here, and we're going to go ahead and type in here recall. And the phase portrait is going to be kind of a visual of how our solutions to this differential equation are going to go. Are they going to increase? Are they going to decrease? So I'm going to draw this out and describe a little bit more about it. So what you're visualizing here is really kind of the y values that exist. And we know that C1 and C2 are critical points for our differential equation. We are told that. So if C sub 1 and C sub 2 are critical points, where C sub 1 is less than C sub 2, you can see it on this axis that this is the case. I'm going to put the up arrow there. And we know that these are critical points. That means that everywhere, whenever we plug in C sub 1 into the right-hand side of this highlighted differential equation, whenever we plug C sub 1 in, it tells us that the derivative or of y with respect to x is going to be 0. So let me write that down. We know that the derivative of y with respect to x when y is equal to C sub 1 is going to be, well, f of C sub 1, but we were told that C sub 1 and C sub 2 are critical points. So whenever y is C sub 1, we know the derivative is 0. So I'm going to draw in possible lineal elements. They will all have slope 0. whenever the height is C1. And likewise, by a similar argument, the lineal elements will have slope 1, or 0, when y is C sub 2. Now, that is not the case for all other numbers so far. We haven't mentioned that we have any other critical numbers, but we did say that that y sub 1 is a solution. So we know we have a curve that exists between, let me highlight this, between C1 and C2. We have a solution between C1 and C2. And that when we plug that solution into the right-hand side of our differential equation, it becomes positive. What does that mean? It means that when we, maybe I'll write this in black here. It means that when we plug y sub 1 in for y, we get that the slopes of our solutions, the slopes of our lineal elements that guide our solutions, are all going to be positive. So I'm going to go ahead and draw out in maybe green here, possible lineal elements. Notice all these are positive, and because I can't run into that horizontal line C sub 2, I'm going to assume that C sub 2 is my horizontal asymptote. Notice on that region, all those lineal elements have positive slopes. So if I were to draw a solution curve on that region, it should look something like this, ever increasing, but never decreasing and never zero. Now, the whole point of this question or this augmented lecture is really to showcase why it will never be zero. Why am I saying that y sub 1, when I plug it in, will never have a slope of 0? In other words, f of y sub 1 cannot be 0. So let's go ahead and take a look at that here. So the last little sentence in green there, why can't there exist, that's what that backwards capital E means, why can't there exist some L in the open interval C1 and C2, so some y value, such that the limit as x goes to infinity, looking at our picture here, just allowing, kind of glancing to the right and looking at the behavior of our solutions, why can't there be some L in this region? I'll draw this in red, or maybe I should have drawn that in gray, actually. Why can't there be an L in this region such that as x goes to infinity, our solution approaches that L? So let's pretend as though that happens and you have something like this. So here's a possible solution. Why is it that the solution doesn't just approach this horizontal, what we're assuming is a horizontal asymptote L? Why am I saying that it has to continue to increase until it gets to the height of C sub 2, not exactly at the height, but infinitesimally close to that height at C2? Why is that the case? Well, we're going to argue this via contradiction. We're actually going to assume that that this is going to happen. So proof by contradiction. Suppose, SPS to me always means suppose. So suppose that there exists an L in the interval C1 to C2 such that the limit as x tends to infinity of f of x, I think that's what we wanted to assume. Let me scroll up. Oh, I'm sorry. The limit as x goes to infinity of y sub 1 of x is equal to that limit L. Suppose that is the case. Suppose this gray curve here does happen. So what does that mean? Well, with that assumption, we could say, well, then our right-hand side function for the derivative, remember dy dx is equal to f of x, or f of y. Dy dx is equal to f of y, yes. So then f of L is just equal to f evaluated at the limit as x approaches infinity of y sub 1, because we have assumed that that's what L is. So far, no flaw in our logic. We're just saying, okay, well then the right-hand side function, recall that the whole problem hinges on that dy dx is equal to f of y. So suppose that the limit as x goes to infinity of y sub 1 of x is equal to L, then f of L is equal to that limit. However, then we can just go ahead and move the limit outside of the function, assuming continuity. So limit as x goes to infinity of f of y sub 1 of x is going to equal that f of L. However, again, looking at this recall statement, f of y sub 1, if I were to replace that y in there by y sub 1, that would mean that we would actually be looking at the derivative of y sub 1, right? F of y sub 1 of x is just dy sub 1 dx. Okay, which is just a fancy notation for y sub 1 prime, so I'm going to use the Lagrange notation rather than the Leibniz notation. So this f of y sub 1, I'm going to replace with the limit as x approaches infinity of y sub 1 prime, technically of x. Kind of a conceptual way you can imagine this now is you're saying that, well, okay, so as x goes to infinity, my y values are approaching a specific height, L, right? Y sub 1 is approaching L, which tells me that their slopes, the slope of y sub 1, is approaching 0. So that means that as x goes to infinity, y sub 1 prime of x will be 0. I'll write that in here. This is equal to 0. This stems from the fact that if it's not 0, then you are not going to tend to a value. You'll go above the value or below the value. And we happen to know, by the way, that the function itself is increasing. So we do know that. We were given that in the problem. In fact, that was the modification we made up here, was that f of y sub 1 is positive. Remember, f of y sub 1 is dy sub 1 dx. In other words, it's the slope of our solution y sub 1, and we're saying it's positive, so that slope is always, or that function's always increasing, and yet we're saying it's approaching a value, so therefore it's increasing but at a lower and lower rate, and so it will tend, its rate of increase will tend to 0 as time goes on. Now, we can then say thus, f of L is equal to 0, and by definition, this implies y equals L is a critical point. Now, this would not be such an issue, except that in the very beginning of the problem, we said let C1 and C2, and I'll use a different highlight color on this, let C1 and C2 be two consecutive critical points. So this whole problem hinged on the fact that C1 and C2 were critical points, but they were consecutive critical points. And now with our assumption that there exists some L in between C1 and C2, that this statement is true, we are now stating that L itself is another critical point and it exists between them. So therefore, this contradicts the fact that C1 and C2 are consecutive critical points, because between C1 and C2, there's another one. So I'm going to go ahead and write that in. So here we have it. Hence, C1 and C2 are not consecutive critical points. This completely contradicts the stated qualities of the situation. The stated qualities are that C1 and C2 are definitely consecutive critical points. And so this contradiction implies that we made a bad assumption somewhere in our proof. Now, if you look through my proof here, there's only one place where I said assume or suppose, and that was that suppose there exists some L between C1 and C2 such that the limit of our solution is going to be that L. So thus, or therefore, there does not exist some number between C1 and C2 such that the limit as x approaches infinity of our solution to this differential equation becomes that number. There's no such number. And that finishes the proof. So it's a very kind of interesting problem. Basically, what this is telling us is that if you have a solution between two consecutive critical numbers, that solution, if let's pretend that solution is an increasing function, that solution will increase all the way to the top, the next consecutive critical number. So this will increase until it gets to the next consecutive critical number. The same argument can be held for decreasing. So if it was decreasing, it would decrease down to the previous critical number. So this lets us know that it will not stop someplace in the middle.